AES structure format, right? So see here, AES working structure is iterative process where we are going to apply every round combination with the 4 common operations. So the 4 common operations which you can see here are substitution bytes, row, shift rows, mix columns, and add round key. So whenever you have this add round key in the as an operation, then this indicates that you are including your key here. Okay. So now coming to the key expansion. See here, key expansion. We have key expansion here. You will be having 128 bits of key, right? So 128 bits of key. Every time you will be taking 32-bit word every time. So that you will be having 128 bits. See, from W0 to W3 means W0, 1, 2, and 3. 32, 32, 32, 32. So you will be having 128 bits in our hand. Now, what is this W0 to W43? See, as we are having one add round key, initial round in the AES is the add round key. So when we are applying this add round key, the key from W0 to W3 is utilized. Okay. From round 1, see, this is round 1, this is round 2. So like this, you will be having round 10, right? So when you have round 1, you have to utilize from W4 to W7. Next, W8 to 9, 10, 11, W11. So like this, round 1 will be starting from W4. So that round 10 will end at W43. So totally, we are in need of 44 words. Got this? So this is one of the gate question which will be asked. How many words an AES working structure required to perform with the ciphering? Okay. So here the key expansion is 44 words, where first 4 words are utilized in the initial round. From the 5th word, you will be including with round 1 to round 10. So this is the basic information you must know about the key expansion. Now, this is done, right? Now, every round, 4 operations. Only 10th round will be having 3 operations. You will not have mixed columns. See, this black box is not there in the round 10. Okay. So the reverse process of, say, once we do with the plain text with the ciphering concept, then you will be getting the ciphertext. So once the ciphertext in our hand, the reverse process will be done with the at the receiver end. We'll start from W40 to W43 in the first round, that is add round key. Then we will shift from round 1 to round 10 in the reverse order, where round 10 here also will not have the basic mixed columns functionality, right? So this is what we are going to apply in the AES working structure. So let us see this, what's happened in the each and every round. Okay. See, there will be a number of rounds as we have just discussed, right? So each round will be having 4 major operations. We'll discuss all this now. Details of each round. See, this is the details of each round, where the input will be carried forward with the state. So whatever the plain text we have, we convert it to 4x4, right? First of all, then that is called as a state. Now, state is the input to the substitution bytes, and we'll get one output. So output state will be given as an input to the shift rows, we'll get one output. So like this, every time we call the state as an input and output depending on the operations which we are performing, right? Next is the byte substitution. So what is happening in the first substitution bytes? See, substitution bytes will be very strong in providing confusion. See, confusion. So we have 2 important things which we are doing in the substitution things. That is nothing but the product ciphering. So that is nothing but confusion and diffusion. So where diffusion dissipates, I mean disappears the plain text combination with the ciphertext, right? Confusion will be giving some confusion with respect to the key combinations which we are applying. So thus we are utilizing substitution here. So we need a table of 16 by 16 for this substitution. So a row of 16 bytes and a column of 16 bytes, a huge table we will be having in the substitution, where we have 4 rows and 16 columns in the DES, but here it is expanded to 16 by 16. Okay. So this 16 by 16 will be replaced with the row and column combination. So let us see this. See, once if we have 95 in our hand, replace by row 9, column 5. Replace by row 9, column 5. So whatever the value which we have at that point will be replaced in terms of 95. Okay. S box is constructed on the transformation of values. See, Galois field which we have discussed in mathematics of cryptography, that is 2 power 8 by default, because 8 bits will be taken all the time as 1 byte, right? So 2 power 8. So if it exceeds 2 power 8, what to do? We have to perform one modulo function. Just to refer mathematics of cryptography once to know this Galois field once. Okay. So this is very strongly resisted with the known attacks. Okay. See, all the known attacks we will not get any time once we perform this. See, this is substitution byte operation. We have 4 by 4 matrix. So you are going to find, see, 1 by 1, right? So x is 1, y is 1. So whatever the value you have at this point will be placed in that box. I'll be showing this to you. So this is a substitution byte table. So just now we have 95, right? 9 and 5. See, 9 and 5. See, 9 and 5 combination, you have 2a. See, when we have 1, 9, see, 9 and 5. This is 9 and 5. So the element is 2a. So that is the reason the previous example which we took is 95 is replaced with 2a in this slide. Okay, in this slide. See, 95 is replaced with 2a. Got this, I guess, now, right? See, that is what we are doing in the substitution byte. See, every substitution byte requires inverse at the receiver end. Substitution operation will be at the sender. Inverse will be at the receiver. So this is the format. If we are doing this at the sender side, as a substitution byte, same thing we should repeat at the receiver side with the inverse operation. Okay. So this table is very important from 0 to 15 and 0 to 15, 16 by 16. This is a table lookup of 16 by 16, right? So that is what we are doing here. See, 0, 0. If you have 0, 0 here, or otherwise we'll take some other thing. 0C. Okay. We have 0C here. Now move to 0C. 0 and C. 0 and C. 0 and C combination, 0 and C. FE is the output, right? FE is the output. Let us see. 0 and C. 0 and C. FE is the output. Yes, right? 0 and C. FE is the output. So in this manner, the state of input will be provided with a substitution byte. So from substitution byte, you will get this as the output. Now, this one we will be providing as an input to the next operation, that is shift rows, right? So shift rows is very simple, that we are going to left shift few operations, left to shift few bits, right? So this is a inverse substitution bytes table. So for substitution bytes, we have one table, inverse we have one table. Next is the shift rows operations. So shift rows operations is very simple, that if you have one state matrix like this, the row 0 will not be touched. It will be same as this. Row 1, shift 1 left side. Okay. So this red block will be outside and added here. Next, second row, these two will be taken out. Okay. These two will be taken out and added to the right side. These 3 will be taken in the row 3. So, okay, right? See, first row is not touched. Second row, this red block added to the right side. Next, red and yellow. See, red and yellow added to the right side. So this is what we do in the shift rows. Very simple concept. Just having state 4 by 4 matrix in our hand. Just start applying. Row 0 means no shift. Row 1, 1 left shift, circular left shift. Row 2, 2 times circular left shift. So row 3, 3 times circular left shift. That's it. Got this? So this is very simple. So inverse is also same thing. We are going to apply in the reverse one. That's it. See, for row, no operations, so same as this. This F2 must be at this end, right, after 26. So that this F2 will shift here, 63 here, 26 here, and this F2 will be added here. Okay, C9 will be added to the right side. Next, FA 6382. FA 6382 added in the left circular shift format. Got this? So the reverse is also very simple. Just we'll apply in the reverse order. That's it. Next, mixed columns is nothing but we will take a constant matrix like this. We will take one constant matrix like this. Okay. We start applying this with our state matrix. Okay. We start applying with our state matrix to get some old matrix. Okay. So whatever the matrix we have, state matrix, apply with this constant matrix, multiply with that constant matrix, and you will be getting your resultant matrix. That's it. But here the small thing is that when we are working with the Galois field 2 power 8, okay, so x power 8 is there, done. Now when x power 8 is there, if you apply with x square, so it will be x power 10, right? But as per the rules of Galois field, it should not exceed 2 power 8, means x power 8. So there we need to perform one modulo operation, which will be reaching to x power 8 and lesser values only. X power 7 accepted, x power 6 accepted, but not greater than 8. So just refer mathematics of cryptography for this concept if you are having any doubt. Okay. See here, mixed column is you take one constant matrix like this, your state matrix. So multiply, you will be getting one output. Very simple. Got this? Now, next one is this is what which we are saying. Next, add round key is nothing but you have to perform 128 bits of key, 128 bits of plain text. You just perform XOR. That's it. Very simple. Okay, this is add round key scheme. 128 bits of your state, 128 bits of your key will be added with the XORed with the values. Then you will be getting some resultant. That's it. This is one performance of AES round. Got this? Now, coming to the key expansion, this is very, very simple. Whatever the key we have in our hands of 128 bits, first represent that in the 4 by 4 matrix as we do for the state matrix in the plain text. So after that, the first row, you go with the W0, first column combination as W0, second column combination W1, third as W2, fourth as W3. That's it. Next, you take one common constant value of word size, I mean 32-bit size. You do XOR and go with the W4. Now, how W5 formed? See, from W4, you work with W1. Okay, W1, W4, XOR W5 will be the output. Okay, W2, W6, XOR will be W6. W7, W3 will be the W7. So like this, we keep on applying until we get W43. Okay, got this. This is a key expansion we do, and each and every round will be having a different key as we do. So this is a graphical representation how we have performed this. Very simple, right? Now, the combination which we are taking, that G value. So that G value we take it as a rot word. So this rot word will be formed from B0 to B4 in the reverse order. So some random permutation will be applied, and with the random permutation, see, B0 is somewhere, okay, B1 is somewhere. So like this, we perform some random permutation, and that rot word we take and we perform with the W0. So that is nothing but about the key expansion module. So this is all about AES encryption. Decryption will be as reverse in the inverse formats, right? So this is what about AES. If you have any doubts regarding AES, just feel free to contact me either in the college or through comments or any media which you are free. Thank you for listening. Bye.